Okay, in this video I'd like to try and find all eigenvalues and eigenfunctions of the differential equation we looked at in the last video. As we saw last time, there's kind of three cases depending on if this number lambda is 0, positive, or negative. We're going to have different forms of answers. So right off the bat, that's what I'm going to do is look at three different cases. So our first case is going to be what if lambda is equal to 0. Okay, so if lambda is equal to 0, that means we have y double prime equals 0. And so our solution is c1 plus c2x. And then if we plug in our initial conditions, we get 0 is equal to c1 plus 0. So c1 is equal to 0. And if we plug in our other initial condition, we get 0 is equal to c1, which is 0, plus c2 times L. Okay. We're going to assume that L is a positive constant. And so if we have 0 is equal to C2 times L, L can't be 0, so it must be that C2 is 0. I mentioned in the last video, factoring is your friend. You want to have a product, so you can say a product equals 0. One of those two is 0, and this is impossible. Okay, so what that tells us is that y is equal to 0 plus 0x. Y is 0, that's the trivial solution. And so this value lambda equals 0 is not an eigenvalue. Okay, so let's jump straight to the second case. What if lambda is a positive number? That's going to be a little tricky to deal with, so we're actually going to rewrite it as lambda is the square of a number. The reason being, I don't want to later on have to take square root of lambda and write square root of lambda a million times. I'll just call it alpha. Okay, so our differential equation now is going to be y double prime plus alpha squared y equals 0, which is going to give us two imaginary solutions, alpha and minus alpha times I. So our solution is going to be c1 cosine alpha x plus c2 sine alpha x. And I'm going to go through the details pretty quick because it looks really similar to what we saw in the last video. If you plug in y of 0 equals 0, we get 0 is equal to c1 cosine of 0 plus c1 plus c2 times the sine of 0, which means we actually get c1 is equal to 0. If we plug in our other initial condition, we get 0 is equal to c1 cosine alpha L plus c2 sine alpha L. Oh, I shouldn't have written that. c1 is 0. Okay, so let's see. Is this trivial? Well, not necessarily. We have 0 is equal to c2 times sine, so either c2 is 0 or sine of alpha L is 0. Okay, well, sine can be 0. All we need is for the inside to be a multiple of pi for some n, some natural number n, or whole number n. Sorry, I'm just going to keep saying wrong words. Any integer n, it could be positive or negative. Okay, anyway, so let's see. If c2 is 0, that means that y is 0, which is the trivial case. So I would much rather have this guy be 0, which means alpha is equal to n pi over L. So if we get this particular alpha, then we will have a non-trivial solution. Y is equal to c2 times the sine of this particular alpha times x. Okay, so what this means is that when alpha is equal to n pi over L, we get y is equal to n squared pi squared over L squared, which is going to be an eigenvalue. This is a value of lambda. Oh, sorry. Whoa. It's a value of lambda that gives us a non-trivial solution, and the corresponding y is going to be, let's see, we said c1 is 0, and so we end up getting c2 times the sine of alpha, which is n pi over L multiplied by x. This is our corresponding eigenfunction. Okay, so let's slide up a little bit and look at the third case, and then we'll come back and talk about some consequences. Okay, the third case is going to be lambda is negative, which again I'm going to rewrite this time as a minus alpha squared. Okay, so in this case our differential equation is y double prime minus alpha squared y equals 0, which means m squared is equal to alpha squared. M is plus or minus alpha, and so we get our solutions are c1 e to the alpha x plus c2 e to the minus alpha x. So I'll plug in my initial conditions. Y of 0 is 0. It says c1 plus c2 is 0, or c2 is minus c1. The other initial condition says if you plug in L, let's see, we also get 0, and I think I'm going to just go ahead and write c2 as minus c1. Sooner or later I'm going to plug everything into everything. Okay, so again we can factor. Factoring is your friend. So either c1 is 0 or e to the alpha L is equal to e to the minus alpha L. Okay, so we talked about in the last video the only way for an exponential to equal an exponential with the same coefficient with the opposite signs is if the exponent is actually 0. And so the only way for this to happen is if alpha is 0 or L is 0. Again, we just keep splitting things up into cases. So let's look at which of these three is actually reasonable. Okay, if L is equal to 0, I don't think that's true because we said at the beginning L is positive. If alpha is equal to 0, then I don't think that's possible either because we said that lambda is a negative number and lambda is minus alpha squared. If lambda was 0, if alpha was 0, lambda would be 0, which contradicts this. We're not actually in case 3. And so I guess it must be that we're in this situation. C1 is 0, which means that C2 must also be 0, which then means that y is equal to 0, which is another trivial case. Okay, so we have a lot of trivial cases. The only cases that weren't trivial were when alpha happened to be n pi over L in this case, and so lambda is n squared pi squared over L squared. Those are only eigenvalues, and these are the corresponding eigenfunctions. Everything else is going to be trivial. So if you want to solve a differential equation that has a non-zero solution, it has to be the differential equation with this lambda, and this is going to be the corresponding solution.